गुड आफ्टरनून बच्चा लोग। ओके ओके। तो हाँ, GNV Sangli is there. Okay, this was your homework actually. So I hope you have done that. Anyone got the answer? JNV Sangli, have you got the answer? What you need to do, calculate the work done by the force. If you need to calculate the work done, then work done should be the area under the graph. Work done should be the area under the graph, and this area can be calculated easily. Either you can see it's a trapezium. It's a trapezium, so its area can be calculated with the formula of area of trapezium. Work done is equals to area of trapezium is what? Half into sum of parallel. I hope you know that. Sum of parallel sides multiplied by separation between parallel sides. So I hope you can see that sum of parallel sides means these two sides are parallel. This is of 15 and this is of 10. This is 10, this is 15. So sum of parallel sides is 25 multiplied by separation between parallel sides from this place to this place. This is the separation now. And this separation is 10. 10. So you will get 5, that is 125 joule. This is a simple question that I hope you have got the answer. Now moving further. That's the answer, 125 joule. This was again the homework. I hope you have attempted it. This is the case of simple case of this force is variable, depends on the x. So work done will be integration, and you are asked to give the displacement is 0 to 2 meter along the x direction. So along the x direction means you need to use fx dx. Put the value of fx is 0.5x plus 10 and solve it. Limit is 0 to 2. You will easily get the answer. And the answer would be 21 joule. This is the basic question. Now, today's topic we are going to start with conservative and non-conservative forces. Okay. Now listen to me very carefully. First of all, I am going to tell you about non-conservative forces. The forces in the presence of which the mechanical energy transforms into internal energy. This is a very bad kind of definition you are getting. Just take an example. Suppose this is a block and capped at a rough surface. and you have pushed the block, like this is you, and you have pushed the block and given it a velocity 5 meter per second. What do you say? After some time, the block will stop now. This block will stop after moving sometime because surface is rough. There will be friction and block will come to rest. So we have given some energy to the block and it ultimately comes to rest. Where does that energy gone? If you lift this block at this end, if you lift this and if you touch it, it will be slightly warmer than the initial situation. So what we can say that due to the presence of friction, the kinetic energy gets converted in the form of heat. Kinetic energy gets converted in the form of thermal energy, or you can say it converted into heat. So what I'm trying to say, this is the non-conservative force. Are you getting my point? The forces in the presence of which, now I am writing the definition, the forces in the presence of which mechanical energy gets converted to internal energy are called non-conservative forces. Then what are conservative forces? The forces in which mechanical energy does not transform to internal energy. What is the meaning of internal energy in this definition? Internal energy here means the heat, temperature. Temperature of the body increases, it means internal energy is increasing. So what I am trying to say that in the presence of non-conservative forces, mechanical energy transforms to internal energy. Have you got that? So one more thing, few examples of non-conservative forces are like our friction that I have told you, like our viscosity. You will study in liquid properties of fluids. These are the examples of non-conservative forces. So if I say that, can you write the definition of conservative forces? Now there are two forces, conservative and non-conservative. In conservative forces, the mechanical energy does not transform to internal energy, and in case of non-conservative forces, mechanical energy transforms to internal energy. I hope these things are pretty much clear to you. Done. Now, there are few basic things that we need to understand about conservative and non-conservative forces. First, properties of conservative forces. I will tell you, you will study after that. I will tell you here. I am going to tell you the properties of conservative forces. Okay. So you can read that after that. Listen to me very carefully. Work done. Okay. Some conservative forces, there are some examples of conservative forces as well, like our gravitational force. Is an example of conservative force. Another example of conservative force is electrostatic force. Good afternoon. Yes, sir. Electrostatic force. So we have just started with the session, conservative and non-conservative forces, and I have given two examples. And in this situation, conservative force is electrostatic force between two magnetic poles. You have heard the north and south pole of the magnets. They are also the example of conservative force. So these are the examples. Now I am telling you the properties of conservative forces. First property says that work done by the conservative force or against the conservative force. You can read it here. Work done by the conservative force or against a conservative force does not depend upon the nature of the path between initial and final position of the body. What they are trying to say, what I am going to tell you is that, for example, this is our ground and this is our roof, terrace. And I have dropped a ball from terrace to the ground. This height is something h. And in the second situation, what I have done, there is an inclined plane. And I have dropped the ball again from the same height h, and ball is again coming to the ground. Done. I have dropped it from here. I have dropped it from here. Ultimately, in both the situations, ball is coming to the ground. In the third scenario, there is a stairs like that. I have dropped the ball this way and it is coming like tip, 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 tip like this. And ball is again coming to the ground. All in these three situations, you can say path followed by the ball is different. In the first case, path is straight down the ground. This time along the inclined plane. This time another zigzag kind of path. But the work done by the gravity in all these three conditions will be same. This is what property of conservative force says. Work done by the conservative force, I am writing it here, work done by or against conservative force depends on initial and final positions only. So initial position is above the ground h height. Initial position is above the ground h height, and initial position is again above the ground h height. So initial position is same. Final position is on the ground, on the ground, on the ground. So in all these three situations, the initial and final position is same. So work done will also be same and does not depend on path. Is it clear to you? I hope this thing is pretty much clear to you, that work done by conservative force does not depend on the path followed. This is a very good application. You will still use it in the class 12th. This is not a limited topic that you are going to study in class 11th and in this particular chapter. This is a basic concept that you will go through with the entire physics. I hope this thing is clear. Second point that I am going to tell you, that work done depends on initial and final position. What if I say that I have dropped this ball from A, it reaches B, and again I throws it up and it again reaches A. So the path will be A to B and then again from B to A. So what if I say calculate the work done in the entire trip? The entire trip is ABA. Can you say that the initial and final positions are same? If initial and final positions are same, then work done will be 0. Work done will be 0. So second property says work done. I am writing these for conservative forces only, no? So don't mess it up. Work done in a round trip is 0. This is again a very good property. Round trip, I think you can understand round trip. JNV ko time, you are pretty much late actually. Please maintain the timetable actually. Work done in a round trip is 0. This is the again second property. Now, third thing is that I can tell you that the definition of conservative forces says that in the presence of conservative forces, mechanical energy cannot be transformed to internal energy. That means mechanical energy will remain conserved. What does it mean that mechanical energy remains conserved? Are you getting my point? So what can you say that in the presence of conservative forces, mechanical energy may remain conserved if I ignore other factors, but due to the conservative forces, there is no loss of mechanical energy. So mechanical energy may remain conserved. This is another good aspect. And the fourth point that I must say that the work done by the conservative forces is completely recoverable. There is no loss in the work. Now, if I say I can put this here, I have removed the ball from ground to the top. The work done can be completely recoverable if I drop it again. If I drop it, it will come with the some form of kinetic energy to the ground. So I can recover this work. I can recover this work. So work is completely recoverable. These are the 4 points. Either I just didn't count how many points are there. You can count. These are the 4 things that should be clear to your mind. Is there any doubt? You can answer it actually if you have some doubts in it. And the persons who are late, they must actually see it from the YouTube actually. It's a very important topic, I must say. And these are the properties of conservative forces. Then what are the properties of non-conservative forces? Just opposite to them. Just opposite to them are the properties of non-conservative forces. So I don't think that it is required to mention here. Opposite to the conservative forces. The work done depends on the path followed. It doesn't depend only on the initial and final positions. In a round trip, work done is not 0. So these things you can change. Okay. So from now, conservative forces, we will remember that gravitational force is a conservative force. Electrostatic force is a conservative force. If I have told you the spring force yesterday, na, that spring force is also a conservative force. That spring force is also a conservative force. I can mention it here. Spring force. Anyone remembered the name spring force? What is the formula for spring force? Anyone? So there is a question for you on the screen. Give it a try and answer me as quickly as possible. Or you can check your answers. What I'm saying, calculate the work done by gravity. Gravity is a conservative force. Gravity is a conservative force. The block is coming from the top of the incline to the bottom of the incline. Can you say that The block displaces by a distance of 4 meters. Block displaces by a distance of 4 meters. So the work done will be force. Can you remember the formula? Displacement parallel. I hope you have remembered that yesterday's punchline was force into displacement parallel. Gravity is acting downward. Do you know gravity is mg? If I can choose g as 10 meter per second square, then gravity will be mg, that is 20. So gravity is 20, displacement in the parallel direction is 4. So F is 20, displacement is 4. This is going to be 80 joule. What if I say the calculate the work done in moving the block upward? In moving the block upward. Then again you will say gravity is downward and the upward displacement is what? 4 meter. Force is downward, displacement is upward. The angle will be 180 degree. So in that situation, work done will be minus 80 joule. Am I too fast or is it okay? Have you got the answer minus 80 for which case? When block was moved upward. Then what if I say total work done in the round trip? 80 joule in the downward motion, 80 joule in the upward motion minus then total work done will be 0. That's what we have learned. What we have learned, the work done by the conservative forces in a round trip is 0. So all things are sorted. Moving ahead, kinetic energy. So this is again a very simple term, kinetic energy. In the first lecture, while defining work, I have told you that work is the method to transfer energy, to transfer mechanical energy. I have told you that. This is the starting line of our session. I hope you have remembered that. And if not, you must know these things actually, and you can recall the lectures. Kinetic energy. So now I'm going to tell you, if you can see, that this is a block of mass m. It is initially at rest. I have applied some force F on it. And due to this force, after moving a distance d, it acquires some velocity v. The thing is, again, I am repeating this thing. The block was initially at rest. I have applied some force. And after some time, some distance d, it has acquired a speed v. So how the kinetic energy is defined? The work done, I am repeating, I will write it in on the screen. The work done required to provide a velocity v to a body at rest is called as kinetic energy. That means kinetic energy is coming from where? Is coming from the work done. So if I write the work required to provide a velocity v to a body kept at rest is called kinetic energy. So kinetic energy is nothing but the work done. So work is the method to transfer energy is what we have justified by this definition. Is it clear to you? So whenever we say kinetic energy, we must know that kinetic energy is nothing but the work done. If kinetic energy is the work done, then its unit will also be joule. And we all know that kinetic energy is represented by K, and its formula is half m v square. Now, I am giving you a task. I am giving you a task that calculates the work done in this situation, and it should come half mv square. What is your task? And please do the homework actually. It's not good that you are not doing your homework, then you will lag actually. Sometimes you will forget things. What I am saying, forget things means forget the logics, forget the concept if you not try your homework. Okay. So what is your task? Calculate the work done in the above situation. For the above diagram, block was at rest, moved after v distance, its velocity is v. Calculate the work done. And it should come half mv square. Clear? So kinetic energy is half mv square. Very simple term, you all know of it. You all know that. I am moving ahead. I think I have mentioned the definition. So, relation between kinetic energy and momentum. This is again a simple term. We know that kinetic energy is half m v square. How many of you know that momentum is mass into velocity? Momentum is mass into velocity. If I multiply this term with m and also divide with m, then the numerator will become m square v square divided by 2m. Is it clear now? M square v square is what? M square v square is what? P square. So K is equals to P square by 2m. So the relation between kinetic energy and momentum is K is equals to P square by 2m. Or you can again write it as P square is equals to 2m is going to be transferred here to Km. How I have remembered this term? Can you resemble it? 2 kilometer. It sounds like na P square is equals to what? 2 kilometer. Not that 2 kilometer. It's 2 kilometer. K is kinetic energy. M is the mass of the particle. But you can remember that P square like P square is equals to 2 km, 2 kilometer. So it's an easy way to remember that. And it's very useful term. Again, I must say actually, this term is going to be used till the end of the class 12. So not to be forgotten. How will you remember that? P square is equals to 2 kilometer. Or you can say P is equals to root 2 kilometer. Anything you can remember. Any term you can remember. This is the relation between momentum and kinetic energy. Now again, there is a very simple question. Every one of you are late. I hope you must know the timings now. So as a teacher, I can scold you next time if you come late. The question on your screen is, the momentum of a body is increased by 20%. This is again a very fundamental, very basic question. But the way of doing it varies from person to person. I will tell you another way. The momentum of a body is increased by 20%. Calculate the percentage change in its kinetic energy. First of all, the two quantities that are being discussed, we must know the relation between them. First thing is very clear. We must know the relation between them, and I know that you all have remembered. Okay. Uh, is it audible right now? Everyone may reply. Is it audible right now? My voice is audible now? Let me check once again. I hope sound should come now. Is it very weak or audible? What are you saying? Audible now? Should I continue now? Okay, it's audible. Everyone says audible. Okay. In place of yes or no, you can write audible or non-audible. Okay, sure. Okay. So we must know the relation. So we know that P square is what? 2 kilometer. P square is 2 kilometer. That's what we have learned up now. In the previous class, once I told you 2 and m, these are the constant. Mass and 2 is a constant. So we can write that P1 square divided by P2 square is equals to K1 by K2. Are you okay with it? P1 square by P2 square, because 2 and m are constants, they can be omitted. I have told you, I have given you complete lecture on that. Okay. So now, momentum is increased by 20%. What if I say that initial momentum is 100? Then final momentum will be 120, na? Because it is increasing by 20%. 100, then increasing by 20% means 120. So P1 and P2 are known. So I can say 100 over 120 square is equals to K1 by K2. You can divide that. If you divide it 5 and 6. If you square it, it will become 25 by 36 is what? K1 by K2. This is again a standard method to solve such questions. Now I will say we need to calculate the percentage change in kinetic energy. Again, the initial kinetic energy is 25. The final kinetic energy is 36. How much it has increased? It has increased from 25 to 36. Can you say that it is increased by 11? Can you say that now it is increased by 11? So how you calculate the percentage? First of all, you will calculate the change. Change is 11. What is the initial kinetic energy? 25 multiplied by 100. This thing is very much new to you, I hope, that you have calculated the ratio. Initial kinetic energy is 25, final is 36. How much it has grown? It has grown from 25 to 36. The value in grow is 11. So change in kinetic energy is 11 divided by the original kinetic energy 25 into 100. You can divide that 4. So that is 44%. What? Increase. This is what? Increase. Good afternoon, JNV Pune. Good afternoon, every student of JNV Pune. Okay, so is it clear to you? 40. This concept is very good. Otherwise, it should be very lengthy. So I hope you got that right. Okay, moving ahead. I hope, let me check the time first of all. We still have 4 minutes to continue. Okay, so there is again a very most important theorem. Most important theorem for every exam, whatever it may be. The theorem says total work done on a system, on a body, total work done is equals to change in the kinetic energy. Total work done is equals to change in the kinetic energy. Total work done, what I say, if I say, let's say this is a block and the surface is rough, I am pulling this block by this force F, then friction must be acting on this now, in this direction. Then what is the value of total work done? Who is going to be work? This force is providing some work. This friction is providing some work. And you need to check whether normal reaction is doing some work, whether gravity is doing some work. The sum of all these work done is equals to the change in kinetic energy. So work done total means you need to check all the work done, all the sources of force, and the total work done is equals to change in kinetic energy. You must write work done total is equals to K final minus K initial. First of all, you need to remember this thing. Work done total is equals to change in kinetic energy. It should be like that. Now, to boost this concept, I have given a very simple example on the next slide. Okay, the question says, have a look at that question, and because time is very less, I am just rushing it out. The ball is of 1 kg mass. It is dropped from this point with a velocity 2 meter per second in the downward direction, and the ground is 40 meter. Calculate the kinetic energy of the ball after reaching the ground. You can solve it easily by using kinematics. This is simple one-dimensional motion. You can easily solve that from there. But now here I am going to tell you the work energy method. Work energy method says work done total is equals to K final minus K initial. Let's check the forces. Gravity is there now. Gravity is there, mg. Mg is 10. Mass is 1, g is 10, gravity is 10. There is no other force acting on the ball. So work done by gravity is equals to K final minus K initial. K initial is what? Half m. V square is what? 4. Velocity is 2 na. So V square is 4. 2. So work done by gravity, force is 10, displacement is 40. Is it 400? Gravity is downward 10, displacement is downward 40. Both are in the same direction. Then work done is force into displacement, that is 400, is equals to K final minus K initial is what? 2. So K final is 402 joule. They can ask you the final velocity. If you know the kinetic energy, can you solve the velocity? Half mv square, you can solve the velocity. This point is initial and this point is final. Is it clear to you? Actually, class was of 3 to 3:40. I think we should wrap it up. Quickly reply whether is it understood to you, all things are clear to you. You can watch the YouTube video if you want to. The persons who are late, they can watch YouTube live or YouTube from the YouTube. You know the channel name, I think. So just quickly reply whether the things are clear. Are you getting my language, my tone, anything you want? You can write it here within a second, and I am ending the meeting. Okay, once more, which topic? The work energy theorem or this question? Okay, I am repeating this question now. Question, okay. Let's see. Should I have, no, I don't have a blank sheet. Okay, the ball is here at point A and it is going to be reached at point B. So what I need to do, we need to calculate the kinetic energy at B. That's what they have asked. So what I say, work done total is equals to change in kinetic energy. Change in kinetic energy. So work done total means who is going to work on the ball? There is only one force present, that is gravity. And gravity is what? Mg. And mg, if you calculate, this mg is going to be 10. m into g, mass into g. M is 1, g is 10, so mg is 10. So force is 10 Newton. Displacement is 40 meter in the downward direction. So the work done by gravity is force into displacement. That is 400 joule. K final minus K initial, which is final point B. At this point, kinetic energy was asked, and initial kinetic energy is at A. If you calculate the kinetic energy at A, it will be half, mass is 1, and velocity square. Velocity was 2. So if I square it, it will become 4. You can solve it and it will be 2. So K final will be 2 can be transferred there. It will be 402 joule. Is it okay? I think its name should be correct. Acer, is it correct? Yeah, very, very good. So I am ending the class here. Hope you will join on time tomorrow. And I will wait for you for 1 minute. And after that, we will start the class. So be present on time. Thank you, everyone.